To substitute or not to substitute? That is the question. Join me as we explore the third of the solid principles, the Liskov Substitution Principle, today on Codesday. So, the Liskov Substitution Principle was introduced originally by Barbara Liskov in a paper co-authored with Janet Wing in 1994. The definition itself is quite mathematical and very terse, and at first glance quite hard to digest and understand. So it goes something like this. Let phi of x be a property provable about objects x of type t. Then phi of y should be true for objects y of type s, where s is a subtype of type t. Like I said, it's very hard to digest, but what it's basically saying is that if you have objects about which you can make a certain statement, then sub-objects, like classes derived from these original objects, should have the same property, have the same trueness about them. So, for instance, like we will see in the code next, is we have a base class called fruit, out of which we've got derived types like banana, apple, orange, and so on. So whatever we can say about the fruit in general must also hold true for any derived fruit. So if we can say any fruit is blendable, we can make smoothies out of it, then we have to be able to say the same thing about any derived fruit. So if you give me an apple, I can still make smoothies out of it. If you give me a banana, I can make smoothie out of that too, and so on. So this is the Liskov substitution principle in a nutshell. We will go now into code and we will see examples of code that respects the Liskov substitution principle and how we can break it, because by breaking things is how we learn new stuff. And it's fun. All right, so today we're going to start off with a slightly different approach. We have here some code that actually works for a change. It respects the Liskov substitution principle out of the box. So what we want to do is run it, see that it works, prove that it works, understand why, and then we're going to think of a way how to break it. Because if you understand how to break things, then you understand how they work. All right, so let's see this code in action. So now if I run this, we should get an output, okay, a console log. So let's walk through the code and see what happened here. So the story behind this is that we want to make smoothies out of fruits. So we have a blender class to which if we give an instance of a fruit, then our blender knows how to make a smoothie out of that. So in this example, we passed in a new banana object, disguised as a fruit because banana inherits from fruit. Because the fruit class has this method peel on it, the blender was able to call peel on our banana and got back a peeled fruit, another base class, with which it managed to make a smoothie. What we care about is this method right here. So why is this method so particularly important? Well, this method is part of the contract between the blender, the client class, and the fruit class, the base type of our hierarchy. And our hierarchy right now is made up of this fruit base class, which is just an abstract class with an abstract method on it. And we've got this particular instance of a fruit here, the banana, which gives us back an instance of a peeled fruit, in this case a peeled banana. So why is this working? It works because the Liskov substitution principle was applied here, and we were able to substitute at runtime a base type with another specific type, right? The banana in this case. So let's see how and if there is a way for us to break this principle, right? To violate the Liskov substitution principle somehow. What could we do to somehow make this pattern, this Liskov substitution principle, not work in practice? Well, obviously, whatever we want to pass in as an argument to the make smoothie method has to inherit from fruit, right? There is no other way around it, because if you're trying to pass some, I don't know, new object in here, obviously this doesn't compile. It has to inherit from fruit, okay? Or maybe we could not return a peeled fruit. Well, again, that's kind of hard because the method says it has to return something of a peeled fruit. And again, the peeled fruit is an abstract class from which currently we inherit a peeled banana. So again, it's kind of hard to break things that way because we have to return something which inherits from peeled fruit. There is no way around that. However, in C#, there is another way you can return from a method. So you can either return something, just like we do here, or throw an exception. Let's see what would happen if we created some sort of inherited type from fruit, just like the banana here, and make that throw an exception when we call the peel method on it. So I have some code I prepared here earlier. So let's go through that. And if I uncomment this code and now run the application, let's see what happens. Okay, so the banana case works as expected as before. But when we're trying to pass in an apple into our blender, we get this log, which says, okay, the blender says I trust the contract because it's a fruit. Therefore, I want to tell the fruit to peel itself. However, the implementation of the fruit base class, in this case the apple, says I'm too sexy to be peeled. So it cannot or will not obey the contract. So let's see what this contract is, because until now we said interfaces are contracts, but there is another type of contract, if you will. It's the sum of all the public methods and properties and public fields on a given class. If you think about it, an interface exposes the same public methods, but for a family of classes, a family of objects. Whereas a single object without an interface on it, it also has its own contract, which exposes to the world, because otherwise you wouldn't be able to interact with that object if it didn't have any public methods or fields or properties. So in this particular example, the contract is exposed or advertised by the fruit base class. And in this case, the contract is constituted of just one public method. And all inheritors from the fruit class have to obey this contract, have to fulfill this contract. All right, so if we take a look at the apple class, nothing too surprising here. All it does is throw an exception. Now, why am I saying that throwing exceptions is a violation of the Liskov Substitution Principle? Well, because at runtime, the client has no idea who's working with, right? He has no idea who's behind this fruit base class. It can be a banana, it can be an apple, it can be anything. So the contract does not expose the information that, hey, if you call this method, you might get a result back, but you also might get back an exception sometimes. At least not in C#. You cannot decorate your method with some sort of attribute or something that exposes to the client of those methods that they might throw exceptions. However, there are programming languages that support this feature to announce to the world that, hey, if you call this, you might get back an exception. And even in the Microsoft world, in C#, Microsoft had at some point a library called Code Contracts, which was supposed to implement in C# or bring into C# the design by contract pattern, which comes from the Eiffel language from Bertrand Meyer. You heard about him in the previous episode. Okay, so how do we fix this thing? So the problem is that the contract is not explicit enough so that the client, in this case the Blender class, knows what to expect when calling the peel method. So there are two ways we can fix this. The first way involves changing the hierarchy of classes, and the second way involves changing the type, the return type, basically, okay, of the peel method. Okay, so let's sketch out a small diagram that would clarify our strategy here a bit. So let's switch back to Microsoft Whiteboard here. And we're going to understand the current situation for a start. So we've got the Blender class here, our client, which references through the base class our derived types at runtime, either the apple or the banana. So what we have to acknowledge here is that the relationship between the blender and the fruit family of classes is not the correct one. Obviously, we cannot make smoothies out of any fruit. The apple was forced to inherit from fruit because presumably it inherited some desired behavior, but in this way it got mixed up in the make smoothie functionality of the client class. So it's not its fault it cannot fulfill the contract. It's here by mistake. So what we want to acknowledge is that the blender does not blend, is not capable of making smoothies out of any fruit. It's only from a particular few. And we have to express this thing in code. So the way to do that is to make another base class. Let's call it blendable. And make the banana object inherit from this class. And we'll make this class inherit from the fruit class. And now we have to change the relationship between the client, the blender class, with the actual family of fruits. So we cannot make smoothies out of just any fruit. We can only make smoothies out of blendable fruits, which contain the method peel. So we have to move the method peel from the fruit base class to the blendable base class so that the apple is no longer blendable or doesn't have the peel method on it. So let's see this in action in code. So what we want to do is come in here. I'll just make a copy of the fruit base class and call this blendable. Right? It will contain the peel method. We'll take it out from the fruit base class. And now let's fix the inheritors. So the banana inherits from the blendable class and it now has the peel method just like before. However, now the apple still inherits from fruit, but it doesn't have the peel method on it anymore. So now the blender does not operate on fruits anymore. It only works with blendable objects. Hence, this code does not make sense anymore, which was the whole problem in the first place. Like, we cannot make smoothies out of apples, apparently. So now, if we run this, obviously it works fine, just like before, for the banana anyway, but now we cannot even compile the code when we're trying to pass in an apple, because the blender does not consume fruits anymore, not just any fruit, but only blendable fruits. So I reverted the code to the previous situation. We're back to square one where the banana and the apple inherit from fruit and we don't have the blendable class anymore because we've seen one way of fixing the problem. Now let's look at the second way of fixing the problem. And the second way implies, like I said, changing the return type of the peel method. So let's see how that goes. So in order to understand the next kind of fix is to realize something about the current contract. The current contract is simply too rigid. It advertises that whenever we call the peel method on a fruit, we guaranteed get back a peeled fruit instance. And that is simply just not true. Obviously, in the case of an apple, we don't get back a peeled fruit, we get back an exception. So what we want to do in the code is to express the potential to the client in a clear and transparent way that when they call the peel method, they might not necessarily get back a peeled fruit. They might get back something else. And we're able to do that with the help of a library which exports a kind of container into which we can either put a peeled fruit instance or return back an empty container. So let's see what that would look like in code. What we have to do is come down here in the fruit base class and we have to change the return type. So instead of a peeled fruit, we return a container which could carry a payload of type peeled fruit, but it might also be empty. So for that, we'll be using this this container type called maybe. Okay? And this is a library I wrote. You can find it on GitHub. I'll put a link down in the description. But obviously on the internet there are other libraries which do exactly the same things. So feel free to look around, check this out, check other libraries like this out, and yeah, play with them, see how they feel. But the basic concept here is that we're wrapping the return type into this kind of container, and this will allow us to write conditional code without writing if statements. You'll see that in a second. Okay, so we wrapped our return type, the peel fruit, into a container. Okay, what do we do with this container? Well, first of all, let's fix the inheritors. So now the banana does not return simply a peeled fruit anymore. It has to return this peeled fruit in a container. So we want to do, so there's two static methods, static constructor methods on this maybe class. Some will represent the container having a payload containing an actual value, whereas none is going to represent the empty container, but of a specific type, in this case, the peeled fruit. We'll see how that works in a second. So here we want to return the container with content. So we choose the sum overload, and we place our peeled banana in the container. But we also have to specify the peeled fruit as a generic argument type, because C# is not able to infer the typing here. Now, on the apple class, obviously the signature is the same, so we have to have the same code in here. However, instead of returning an exception now, we want to return, remember we said maybe none of peeled fruit. Okay, so basically we've told our container, hey, we want to create a container which potentially could contain a peeled fruit. It just so happens that it doesn't contain any. All right, so we managed to package our peeled fruits in some sort of container, the maybe type. So before we change the code up here, I want to draw a little diagram to see exactly what we're dealing with here. So let's switch back to the whiteboard and let's see what we've got. So on one hand, we've got here our peel method, right? Which until now, it returned a peeled fruit. Ta-da! Now we changed our peel method to return a peeled fruit in a container. Okay, so what? What can we do with this containerized peeled fruit? Well, for starters, this container allows us to write conditional code without writing if statements. And that is good because it saves our code from looking like a Christmas tree where you have ifs within ifs within ifs and so on, and treats edge cases for us. Like, hey, if you only care about the case where you actually have a container containing something, like in this case a banana, then you do something with it. Otherwise, you don't want to do anything in particular with it. You just want to just give back the same type of container to the calling function. So let's see what that would look like. So the interesting thing about this container is that once you put a value in, you can never get back that value out. So it's not like now we can go and say, hey, Mr. Container, please give me back my banana. But what you can do is you can inject into the container functionality in the form of Lambda functions, which can operate on the contents of the container, if any. And by doing this transformation, this operation inside the container, you get back the same type of container with potentially a different type of content. So how can we make use of this here? Well, now we have a container with a potential peeled banana inside of it. What we want to do with this container is to transform it in another container, well, the same type of container, but with a smoothie inside if there was a banana in the first container in the first place. So if we get back a container containing a banana from the peel method, we want to apply some sort of mapping function, which would give us back another instance of the same type of container. We're still working with that maybe type, remember? But now in that container, we would have a smoothie, right? So if in the original container, we have a peeled fruit, then by applying this mapping function, we would get back a new instance of the same type of container, but now containing a different thing. If the container was empty, we would receive back still an empty container. Let's see that in action in code. So if we switch now to the code, let's see how we can make use of all this stuff. So first of all, let's rename this so we know what this variable is pointing to. And we want to apply that magical mapping function we've been talking about. And in this scenario, in this library, for instance, the select method is the one that's doing the mapping. And this might look familiar to you because you've seen this while working with lists. Lists are the same type of container like the maybe container is. And these things are called monads. You might have heard of them. If not, that's fine. Even if you heard of them and you're scared, that's also fine. Don't worry about it. You've been working with monads your whole life and you didn't even know it. So we want to apply the mapping function to our container, specifying that if indeed it has a peeled fruit, we would like to return back a new smoothie of said peeled fruit, right? So if we store this in a variable, smoothie maybe, okay? So if we look now at the smoothie maybe variable, we see that now that we have a container of type maybe again, but with a different potential payload. Until now, we had a maybe of peeled fruit, but now we get a container maybe which might contain smoothies. So now we want to return this smoothie maybe. However, well, let me comment this out. However, now we have to change the signature of the make smoothie method itself. And I'm going to explain why this makes sense in a second. Well, this makes sense because the contract has changed. The relationship with the blender with its family of fruits changed. Hence, the relationship between the blender and its clients has to change because the blender is no longer able to fulfill the same kind of rigid contract. Until now it worked because the fruits guaranteed that whenever you call peel, you get back a peeled fruit. Well, apart from the apple, okay? That's a special case. Therefore, the blender was able to make the same promises to its clients. So, hey, if you give me a fruit, I guarantee I'm going to give you back a smoothie. However, the situation changed now. The fruits themselves are no longer able to promise that whenever you have a fruit, you will get back a peeled fruit. Now you might get back a peeled fruit or an empty container. Now, since this relationship changed, it makes sense that also the relationship between the blender and its clients has to change. So the blender now has to change its post conditions, right? It cannot promise itself that whenever you give it a fruit, it will guaranteed give you back a smoothie. It has to relax its post conditions because the fruit family relaxed its post conditions. So it's no longer able to make a stronger promise than the promise it gets back from the fruit family. So now, if we look at the banana smoothie, it's not simply a smoothie anymore. We might as well call this a banana smoothie maybe. And if we look at this variable, now we have a container of type sum which might contain a smoothie, and it actually does. Is sum true? Therefore it has items, it has an actual value. It contains a smoothie object which was created out of a banana. But now if we try to do the same thing with the apple, let's see what happens in this case. So now if we look at the apple smoothie maybe variable, you see it's of type none and it doesn't have any items, it doesn't have any values. So there you have it. Two ways of fixing the Liskov substitution principle. The first one had to do with changing the relationship between the blender, the client class, and the fruit family of classes. You couldn't make smoothies out of any fruits, but only a particular few. And the other kind of fix implied changing the return type from throwing exceptions to operating with this container type object. So, we've seen the Liskov substitution principle in action. We've seen code that obeys the principle, and we've seen how to fix code that doesn't. The purpose of the principle is to offer guidance when designing hierarchies of objects related through inheritance. By analyzing the code through the lens of this principle, we can create code that is provable correct and makes sense semantically, not just syntactically. Thank you everyone for watching, and if you found any of this remotely interesting, please consider leaving a like, comment, and even subscribe. Thank you everyone, and see you on the next episode of Codesday.